All right, thanks for coming to the exam review today. So you've seen one of these recorded or online, so it's same story here. Feel free to interrupt with questions anytime. I don't know what the mic situation is here, but it feels like anything picked up. Hopefully you can hear me all right. And what I'll do is I'll start with a review of one topic that I haven't covered yet that I just want to make sure you're clear on, and then I'll go through the 20 questions that are in the packet. Usually it works out best if you're able to wait till the end of each question to ask your questions, because often you anticipate what I'm going to say, and then I have to say it anyway. So, but feel free to stop at the end of any question for clarification on that problem or anything that you think might be related to that topic that you're just not sure about. All right, so the first thing I want to review, though, before I get into the problems, are shapes of hybrid orbitals. There are a couple questions in the exam bank related to this, and I, don't think that it's likely it'll come up for you because there's a lot of questions in those banks. But just in case you see one, I don't think I covered this in class. All right, so what we're going to have here is two possible ways to frame this. So one would be the shape of an individual hybrid orbital, and whether it's sp, sp2, or sp3, they're all kind of roughly similar to each other. There would be subtle differences, but we don't expect you to really spot those differences. Just know that what you're doing when you make a hybrid orbital is you're taking an s orbital that's spherical, a p orbital which is figure 8 shape. I hear my voice coming from somewhere and it's starting to freak me out, but I'll get used to it. All right, so you have an s and a p orbital, or if it's sp2, it would be an s plus 2 p orbitals, s plus 3 p orbitals, but some combination of s and p that you're mixing together to make hybrid orbitals. And so they all have sort of similar shapes. The s orbital has aligned, in phase interaction with part of the p orbital. It's out of phase with the other part, and so you kind of get this distorted figure 8 shape for all the hybrid orbitals. We have a big lobe and a small lobe. So again, they're all going to be kind of similar. There'd be the shapes of the lobes would be more or less uneven depending on whether it's SP, SP2, or SP3. We don't really expect you to know that difference. Just know that they all have approximately the same shape. One big lobe, one small lobe. And this would be the one that would overlap with other atoms to form bonds. Now, the other way that we could ask this is, what is the shape or the arrangement of a set of hybrid orbitals, where it's not just an individual sp, sp2, sp3 orbital, but all 2, 3, or 4 of them. And again, those are going to arrange themselves in the geometries that they correlate with. So if you had a set of sp orbitals, it would look like this. You'd have 2 of these orbitals that have approximately that shape, and they're going to be arranged 180 degrees apart from each other. So this little lobe here would be kind of buried in the region between the two, but the two main lobes, the big parts, would sort of stick out in opposite directions. sp2, similar story, but now there's 3 of them, and they arrange themselves trigonal planar. And then sp3 is that characteristic tetrahedral geometry where 4 of those orbitals would all point in the directions of a tetrahedron. So just be aware of that possibility coming up on the exam. It's not a big thing that we're going to emphasize. We didn't really talk about shapes of hybrid orbitals in classes, and that's kind of what they look like. We should know, of course, this part down here, how the hybridization correlates with the molecular shape and the electron group arrangement, but just putting it in this context is a little bit different. All right, any questions on that topic before I move on to the problems? All right, so let's get right into the problems then, starting with number 1. So the exam is ordered in order of the chapters 4, 5, and 6, and so we'll start with chapter 4 material here. The first one asks about the electron group arrangement and molecular geometry, respectively, for this hypothetical anion SeF3-. So the first thing we should do is review how to draw the Lewis structure. That was a chapter 3 topic, but it is going to be required that you're able to do that for some of the problems on this exam, especially those that deal with shape, hybridization, and polarity are the first few topics that we'll cover. All right, so for this one here, we need a Lewis structure. So we have selenium, and we have fluorine, and we have a negative charge that are going to account for all the electrons that are present, all the valence electrons. And as a review, we're going to go to the periodic table to figure out how many valence electrons each of those atoms has. I may need to plug in eventually. So anyway, so we have selenium Se is group 6. Let me turn the mic down a little bit. I don't think I need it. Microphone, room volume. All right, let's see if that helps less echoey, maybe. All right, so you have selenium, which is here in group 6, 6 valence electrons. There we go, we gotta do this. All right, let's try that. All right, as long as you guys, if you have trouble hearing me, let me know, but I was getting an echo from the microphone, so this feels better to me. All right, selenium is here in group 6. Oh, it's still doing it. Turn the microphones off, and they're still doing that. Well, I'll never know why. Selenium is here in group 6, and it has 6 valence electrons, and then each fluorine from group 7 will have 7. So remember, the group number here at the top tells you the number of valence electrons that you have. So if we go back to that and start counting, then we have 1 selenium in the formula, so that's going to be 6 electrons. Let me try one more thing. All right, so you have 1 selenium, that's 6 electrons, and then you have 3 fluorines in the formula that are 7 each. And then you have a negative charge, which is going to add 1 more. So a total of 28. That sounds better. All right, so we have 28 valence electrons to account for in this structure. And what we'll do then is arrange them around the central atom, which is selenium. We start with single bonds to the outer atoms. So again, this is all a review of chapter 3, so I don't want to spend a ton of time on it, but make sure we know how to do this well. So we complete the octets then, putting 6 more on each of those, 2 from the bonds, 6 more as lone pairs. At this point, we take stock of how many we've used. That's going to be 24, because there's 3 complete octets. We have 28 total that we can use, and so we're going to put 4 more on the central atom as lone pairs, so 2 pairs on the central atom. So this whole thing is negatively charged, if we want to keep track of that. So that would be the Lewis structure. Now what this question asks us to do is determine then the corresponding electron group arrangement and molecular geometry. So the electron group arrangement is going to be determined by the total number of electron groups that are around the central atom. An electron group is going to be counted as an atom that's bonded to the central atom or a lone pair that's on the central atom. So any of those would count as 1 electron group. Or we could also do this in the AXE notation. So our central atom A, and then we have 3 bonded atoms, so it would be X3, and then 2 lone pairs on the central atom, so E2. So however you decide to do that, you would count a steric number or a total number of electron groups of 5. So there's 5 things on the central atom, 3 bonded atoms, 2 lone pairs for a total of 5. And so that number is going to dictate the electron group arrangement. Any combination of 5 is going to give the same electron group arrangement, which would be the trigonal bipyramidal one. All right, and that would be the electron group arrangement we get anytime the number of atoms and the number of lone pairs adds up to 5, like it does here. Now the specific geometry though, or as we call it, the shape sometimes, that's going to be determined by the combination of atoms and lone pairs that we have. So we know that's going to be trigonal bipyramidal, so if we trust ourselves in that, we basically narrowed it down to either C or D. Those are the only ones that have the correct electron group arrangement. We have to figure out then, is it T-shaped or trigonal planar? So when you have 5 electron groups, you're going to do a trigonal bipyramidal arrangement, which is a triangle with 1 above and 1 below, central atom right there. And then, as we talked about, the trigonal bipyramidal one is a little bit of a weird one because it's the only one where it really matters where we put the electrons, and they have to go on the outside of the triangle here. So both lone pairs go there, and that leaves a fluorine there, and a fluorine there. It's turned on its side, but we call it the T-shaped geometry. All right, so there is a table in the notes if you want to, memorize all these combinations. I don't recommend brute force memorization. Try to really be able to start with the electron group arrangement and rationalize the shape in the way that I did. But either way, however you get there, the answer should be trigonal bipyramidal for the electron group arrangement and T-shaped for the geometry. All right, any questions on that or VSEPR? Okay, I'll just keep going then. Please stop me anytime. All right, the next topic here is going to deal also with VSEPR, but we're going to use that then to relate to the polarity of the molecule. So we talked about molecular polarity as another early topic in chapter 4. And what we're asking here is which of the following molecules have a non-zero dipole moment? So we have to be a little bit familiar with the terminology here. When we say non-zero dipole moment, we're talking about a molecule that is polar. All right, if it has a dipole moment, it's polar. If it doesn't have a dipole moment or the dipole moment is 0, that means it's nonpolar. All right, so that's going to be what we're looking for here, is which of these are polar. All right, and if we look at the molecules that we have here, all of these have just central atom and one type of outer atom. They're all fluorine compounds, as it turns out. And so there's some simple patterns we can use to predict polarity. It's really just based on the electron group arrangement and the number of lone pairs on the central atom. So if we look at NF3, I'm not going to go through all the details of drawing Lewis structures and all that, but what you would get for NF3 is an AX3E arrangement. So it's going to have 3 fluorines plus 1 lone pair in the central atom. And so anything that has 1 lone pair in the central atom, regardless of what other things it has on it, is going to be polar. So if you have a single lone pair in the central atom, it will be polar. So that one we can label as polar. So again, that would be, I'm not going to draw all the geometries, but it would look like this. AX3 with 1 lone pair, and that would be a polar geometry, trigonal pyramidal. If we go to BF3, what we would find for this one is that it's also AX3. You can tell from the formula how many X's there are. It's how many atoms there are in the central atom. There's 3 fluorines, so it's AX3 something. But this one is going to be just AX3 or AX3E0, if you like to write that in explicitly. So any of the geometries that have no lone pairs on the central atom and only one type of outer atom, fluorine in this case, those are all nonpolar. So 0 and 1 lone pairs are usually the easier ones to deal with, because if there's 0 lone pairs, it's nonpolar as long as there's only one outer atom type, and if there's 1 lone pair, no matter what, it has to be polar. So those two are fairly straightforward if we get the Lewis structure right. The next couple are not as obvious, though. We have xenon difluoride, xenon tetrafluoride. These are not the most common geometries, but they do exist. And so for XEF2, xenon difluoride, what we would get is AX2E3. Now, one thing that's nice about geometries that only have 3 atoms in the formula, xenon difluoride being one of them, 3 atoms in the formula, it's either going to be linear or bent. If it's linear, it's nonpolar. If it's bent, it's polar. So we just have to decide between those two for this one. So for AX2E3, what ends up happening is it's 5 electron groups, so it's going to be trigonal bipyramidal. We fill all those triangular positions with lone pairs, and that just leaves fluorine there and fluorine there with a central atom. So this would be a linear geometry, which makes it nonpolar. So if you have a linear geometry, one type of outer atom is nonpolar. If it's bent, it would be polar. If we go to xenon tetrafluoride, what we get for this one is AX4E2. So the ones with two lone pairs, there's not an obvious pattern. There's a couple, 2 or 3 different geometries. Some of them are polar, some of them are not. So if you have AX2E2, it's polar. AX3E2 is also polar. AX4E2, though, is the third one we have to consider. And so for this one here, it's helpful to draw it out. So this comes out to be square planar. It's going to be an octahedral electron group arrangement, lone pairs at the top and the bottom, and then you have your xenon and your 4 fluorines in the corner. All right, so this one is going to be nonpolar, and the reason being, as we talked about in class, you basically have opposing dipole moments in both directions. So it's kind of like 2 linear molecules superimposed on each other, where you have all the dipoles canceling out, one in each opposite direction towards each corner. So they all cancel out, so AX4E2 would be nonpolar. And then the last one, SF4, without even drawing it out, what we would get if we did the Lewis structure correctly is AX4E. Again, anything that has 1 lone pair has to be polar, so we don't even have to really think about that one further. So there's also a table in the notes that adds in information about polarity for the different geometries. Again, not my top recommendation to memorize that, but it is helpful to look at and some of the patterns that you see, like 1 lone pair being polar, 0 lone pairs being nonpolar, helpful to know. So we're looking for the polar ones here. So we're going to have NF3, SF4 being polar, and so that's going to be number 1 and number 5. So that should be choice C here. So those are going to be the ones that are polar. The ones that have 1 lone pair in this case are all polar. All right, any questions on molecular polarity? All right, moving on. And then using the same anion that we discussed in the first problem, save us a little bit of time, not have to draw it all out again. What is the hybridization on the central atom in this anion SEF3-? So hybridization also directly correlates with the number of electron groups, or the steric number as I called it at times. So for SEF3 minus, as we already determined, it's going to be AX3E2. And that means we have a steric number, or a total number of electron groups, that's 5. Already talked about that earlier. So then to get the hybridization, you basically need to hybridize the number of orbitals that it takes to arrange 5 electron groups around the central atom. So available for hybridization, we have 1 s orbital, 3 p orbitals, and then up to 2 d orbitals that we can hybridize. There are 5 d orbitals, but only 2 of them are involved in hybridization ever. So we have these orbitals available. We need to use 5 to get a steric number of 5, so we're going to circle the first 5, sp3d. Sometimes you'll see it written as dsp3, so don't be confused by that. They mean the same thing. But anyways, 5 total orbitals hybridized to get 5 electron groups around the center atom. And so that leads us to, again, choice C here. So really, there's only 5 possibilities for hybridization, and it's all determined by the number of electron groups in the central atom. Remember, an electron group is counted as an atom that's bonded to the central atom or a lone pair in the central atom. We don't care if those atoms are singly, doubly, or triply bonded. They just count as one electron group. And the number of those is going to dictate the hybridization. So you have possibilities of 2, 3, 4, 5, or 6. 2 electron groups is sp, 3 is sp2, 4 is sp3, 5, as we just saw, is sp3d, 6, the highest one, would be sp3d2. And so that's going to be really all your only possibilities. And for hybridization, that's essentially the depth we would likely expect you to go into. We're not going to, hybridization is a bit of a confusing topic conceptually. We talked about that a lot in class, but most of the exam questions are going to be just identifying hybridization using this approach here. So any questions on that? All right, onward and upward. So then we're going to go to another major topic in chapter 4, which covered a few different bonding theories. So valence bond theory is the one that deals with hybridization, what we just talked about. The other major bonding theory we covered is molecular orbital theory, which is a delocalized theory of bonding. And so you could have questions on the exam like this one, which are more conceptual in nature. According to molecular orbital theory, which of the following will increase the bond order in a diatomic molecule? So when we have a molecular orbital diagram, and we'll do this again in a little bit in more detail for another problem, but basically we can calculate the bond order. BO stands for bond order, not body order. Sorry, bond order, not body odor in this context. So bond order is going to be 1/2 times the number of bonding electrons. That's going to be the number of electrons in bonding orbitals minus the number of anti-bonding electrons. So it's that sort of competition between those two. So there's basically 4 possibilities for how we can influence the bond order of a molecule. We can either add or subtract electrons from bonding orbital, add or subtract electrons from an anti-bonding orbital. So let's go over those possibilities. So if we either add or subtract, so let's just write all these possibilities out. So if we think about the bonding orbitals first, if we add an electron to a bonding orbital, mathematically speaking, we're increasing this term here, we're adding electrons to a bonding orbital. That will cause the bond order to go up. If we subtract from a bonding orbital, we're going to reduce the number of bonding electrons, and that's going to cause the bond order to go down, mathematically speaking. And then for anti-bonding orbitals, it's sort of the opposite trend. If we add electrons to anti-bonding orbitals, this term here is going to increase, so the whole thing is going to get smaller because we're subtracting that number. So your bonding orbital would also go down in that case. If we subtract electrons from an anti-bonding orbital, we reduce this term, and the whole thing increases. So all those are the 4 possibilities for how adding or subtracting electrons from those different orbitals can influence bond order. So we're looking for the ones that will increase the bond order here. So adding electrons to a bonding orbital would increase Adding electrons to the antibinding orbital, though, that's going to be that one that would decrease it, because that increases the second term here, so that one's not going to work. Removing electrons from a binding orbital, that decreases bond order, so that one we're going to put an X by, and then removing electrons from antibinding orbital also does. So those two there, A and D, would be the two that will increase the bond order. Just thinking about this relationship, I mean, chemically what you're doing is, remember, in a bonding orbital, you have electron density between the nuclei. So if you put more electrons in there, you have more electrons holding the nuclei together. That's why the bond order increases, gets stronger. Antibonding orbitals have electron density outside the nucleus, and so when you put electrons in there, it kind of causes the nuclei to sort of repel each other in some sense, or kind of fall apart from each other. So those antibonding orbitals result in weakening the bond when you have electrons there. So that's one of the key concepts of molecular orbital theory, which was covered in this problem. So any questions on that? Yep.
Can you explain what a bond order is?
So bond order is the number of shared electron pairs between the two atoms. So if you're drawing a Lewis structure, we have the possibility of single, double, triple bond, and that's the bond order. Bond order of 1 for single bond, bond order of 2 for double bond. You can also use molecular orbital theory to calculate that in a little bit, more of an abstract way, using the molecular orbital diagram and how many electrons are in bonding orbitals versus antibonding orbitals, and it means the same thing overall. It's just you can have fractional bond orders in that case, and there's it's a little bit different way of determining it from that, not just drawing a Lewis structure, but it means the same thing. Yep. Any other questions? All right, so number 5, which is a more, practical problem about molecular orbital theory. So we have this cation here called dioxygenyl, and I always forget to fix the spelling error. It's not an action, it's a cation. But anyway, the important part is that it's O2 plus is the formula. So oxygen with 1 fewer electron. So we want to know what is the bond order and the number of unpaired electrons for this ion. So to determine the bond order, we need to figure out the correct electron configuration. How many electrons are in each orbital? And here we're talking about molecular orbitals. And so for the molecular orbital diagram, however you choose to remember this, we need to make sure that we put these things in the right order. So at the bottom is going to be sigma 2s and sigma star. So in these p block elements, like oxygen or nitrogen or carbon and so on, they have 2s and 2p orbitals that are going to be able to mix together and make molecular orbitals. So the 2s orbitals mix together to make bonding and anti-bonding. And then the p orbitals mix together to make both sigma and pi bonding and anti-bonding. In oxygen, which is in the second half of the p block, there's no periodic table, and you keep looking to that side of the room, it's not there. So oxygen is here, second half of the p block towards the right. And so that's going to be one where you would have the sigma 2p orbitals coming first, and then pi. So this is the order of the two that can switch on us. And then the highest ones are going to be pi star and sigma star, also from 2p. So however you choose to do it, it's important for problems like this with molecular orbital theory to remember the order of these orbitals, so we know how to fill them with the correct number of electrons. And then from there, we're going to make sure we put the right number of electrons in. So for O2 plus, we have 2 oxygen atoms, each with 6 valence electrons, but we have a positive charge, so that removes 1. So we're going to have a total of 11 valence electrons that need to go in to this diagram. So now we're going to just follow the normal rules that we use for filling orbitals. We're going to go lowest energy to highest energy. Bottom is lowest energy, top is highest. And we add 2 electrons per orbital before adding to the next level. So we're going to go 1, 2, 3, 4, 5, 6. These ones we're going to fill 7, 8, 9, 10, one at a time to follow Hund's rule, but we still have one more that goes up here. All right, so there's going to be 2 questions then that are involved in this. What is the bond order and the number of unpaired electrons? So bond order is going to be that same formula that we just talked about. 1/2, we start with the number of electrons that are in bonding orbitals. Those are the orbitals that don't have stars next to them, so it's going to be these 2, 4, 6, 8. So all 4 of our bonding orbitals are filled, so there's a total of 8 electrons in bonding orbitals. And then the number of anti-bonding electrons is going to be those 2 there in sigma star, that's 2 antibonding electrons, plus this last one up here, which was in pi star. So 3 of those 11 electrons are antibonding. So it's going to be 1/2 times 8 minus 3, which comes out to 5/2 or 2.5. All right, so this is a fractional bond order of 2.5, which we can have in molecular orbital theory. And then the other question, which is a little bit simpler once we have the diagram drawn, is the number of unpaired electrons. So an unpaired electron is one that doesn't have a partner in the same orbital as it. So these 2, 4, 6, 8, the first 10 are all paired. They all have another electron in the same orbital with them. But then this lone guy up here is going to be unpaired, so there's going to be one unpaired electron. Now there are a couple of patterns you can recognize that can help you on these to at least make sure your answer is reasonable. So the first is that we have two possibilities. Your number of valence electrons is either an even or an odd number. If it's an odd number like it is here, that can be helpful because that means you're definitely going to have a fractional bond order, something 0.5. You have to get the number right, of course, but it's going to have to be 0.5. And then also, if you have an odd number of electrons, the number of unpaired electrons has to be 1. There's no other way to do that in this diagram. So whenever you have an odd number of electrons, you know that there's one unpaired electron, which means that it's paramagnetic, has at least 1. If you have an even number of electrons, you have to look at the diagram a little bit more closely because you could have 0 unpaired electrons or you could have 2. Your bond order is going to be a whole number, but again, you have to calculate it in this way to get the actual right number. There's no shortcut to that. But knowing a little bit about those patterns is helpful to make sure that you're approaching the problem in a reasonable way. So that's a pretty typical. We could ask you for either or both of these. Bond order, number of unpaired electrons are the two most common things we would ask you for a microorbital problem like this. So any questions? Yeah.
So diamagnetic is like no unpaired?
Yeah, so diamagnetic would be no unpaired electrons. So if we didn't have this last one here, that would be diamagnetic, but adding one more unpaired would make it paramagnetic. That's right.
Can you just explain again when it switches?
Yeah, so the ones that switch on us are these two here. So this ordering where you have sigma 2p first and then pi 2p, that's going to be true for the second half of the p block, O2, F2, or if you did neon, which does not really exist, but if you were to do it for any of those p block elements, those last three columns, it would switch then to this. Let me do it in a totally different color so I don't confuse you guys. If you can also have it in this order where pi comes first and then sigma, and that's going to be the first half. So I guess start with boron, B2, C2, or N2. So anything in those first three columns of the p block. So that's where it switches. It's not going to affect the bond order that you calculate if you forget to do that, but it could affect the number of unpaired electrons if you don't get that ordering correctly. All right, anything else? All right, so that concludes chapter 4. So I do attempt to make these reviews kind of representative of at least the distribution of topics on the exam. So we have 5 questions on chapter 4 here, so that's what you can pretty much expect on your own exams. Now we're into chapters 5 and 6, where we have sort of an abrupt switch towards a lot more numerical and quantitative type problems. So here we have a hypothetical element, TT, which just by coincidence has my initials, and it has an atomic mass of 132.2145. If it has 2 stable isotopes with the mass numbers and the actual masses given here, what is the percent abundance of the heavier one, the 134 isotope? And as in most numerical questions, it would specify how to enter the answer, 2 decimal places, no units. All right, so for problems like these that deal with atomic mass, there's just one equation that you have to focus your attention on, which is just the definition of atomic mass. It's the weighted average of all the isotope masses. Typically, we'll only do it for 2 isotopes, especially in a problem like this where you're solving for some unknown that's not just the atomic mass itself. So you'll have the abundance of the first isotope times its mass plus the abundance of the second isotope. And in this formula, it's going to be fractional abundance, which would be percentage divided by 100. Basically the relative abundance. So abundance of each times the mass. And if you had more than 2 isotopes, you would just keep adding those together. Here we only have 2 to worry about. So in this problem here, what we have is a little bit different situation where we're solving for the percent abundances. So we have a given atomic mass in this problem of 132.2145. And then the individual isotope masses are given as well. So if we call this the 131 isotope, that's going to be given to us in the problem. That's that number. This mass is given to us. But what our unknowns are going to be are the fractional and percent abundances of both. We don't know either of those. So we'll call those our two variables x and y. And in problems like this, if you have two unknown abundances and you're trying to solve for one of them, you need a second relationship. And the second relationship is just going to be that the sum of the fractional abundances has to equal 1. Or the sum of the percentages equals 100, but in this form we'll use the fractional abundances to start with. And so that relationship is going to be always useful for you if you have both of those being unknown. So what we're going to do in this problem here is just a little bit of algebra where we're solving for y. So y is what we're trying to solve for here. We want the fractional or percent abundance of the second isotope, if we call that the 134 isotope here. And so what we're going to do is just rearrange and say that x is equal to 1 minus y. And we're going to replace x with that. All right, so I'm going through the algebra now a little bit, but I don't want to spend too much time on that. So our given atomic mass is 132.2145. The mass of the first isotope is 130.9856. All the numbers are given to us in the problem. And that's going to be multiplied by the abundance, which is x, but we're going to replace x with 1 minus y. And then the second mass is 133.9767. Come on. I want to erase that period. Come on, please erase. There we go. 9767. I'll get it right eventually. All right, and that's the mass of the second isotope, and that's going to be multiplied by that abundance, which is just y, what we're solving for. It doesn't matter what you call x and what you call y or which one you solve for first. Those are all arbitrary, but we're solving for y here as I've defined it. And so then we just do some algebra to solve for y, which I'm not going to go through in a lot of detail. But y is representing the abundance of that isotope that we're looking for, 134 isotope. And it comes out to 0.4109. That's the fractional abundance, but we want the percent. So don't forget the difference between those. Anytime you want a percentage, you have to multiply the fractional abundance by 100. So 0.4109 times 100 comes out with 2 decimal places as 41.09%. You would just enter the number 41.09 into Blackboard. All right, so if you do a problem like this, there is a decent amount of algebra involved, but your answer, of course, should be between 0 and 100. If it's outside of that range, you mess something up. You'll just follow this equation here and set up for and try to find whatever your unknown is. So your unknown can be really any of these terms. We could just ask you to find the atomic mass, in which case you just apply the equation and you're good to go. Other cases, maybe one of the masses is your unknown you have to solve for. So whatever the variable is can change, but it's the same relationship that you always use. All right, questions on that? Okay. All right, and so the next problems are going to deal with sort of mole relationships and then getting into stoichiometry, which is really the major topic of chapter 5. So how many moles of sodium ions are present in 65.65 grams of sodium phosphate? So if we're going to do this, we have a mass given to us and we have a number of moles. So we are going to have to use the molar mass at some point. And to do that, we need the correct formula. We need the correct formula really for two reasons, both for that part of it, the molar mass, as well as to figure out how many sodium ions there would actually be there. So we need the correct formula. So a quick review of ionic formulas. We have sodium and phosphate. Sodium is in the first column in the periodic table, Na, and so it's going to have a +1 charge whenever it makes an ionic compound. So the charge of our cation is +1. We have to remember our polyatomic ions for this exam. They come up a lot, especially in chapter 6, but also possibly in any part of the exam they could be there. So phosphate, we have to remember, is PO4 3-. All right, so if you're a little bit rusty on your polyatomic ions, spend a little bit of time reviewing them. The common ones that you see all the time: sulfate, phosphate, nitrate, stuff like that. All right, so that's going to be the charge of the ion. So if we want to get the correct formula for the compound, we have to balance those charges, which, as we talked about before, you can do this way if you want. So we just make the charges into subscripts, and so what we end up with is sodium 3PO4. Na3PO4 is going to be the formula for sodium phosphate. So if we're going to do a mass to mole relationship, we're going to need the molar mass then of this compound, which is just the sum of all the atomic masses. And so we have 3 sodiums in the formula, and the atomic mass for sodium is 22.99. It's that number below it on the periodic table. So we have an atomic mass of 22.99 for sodium. We have 1 phosphorus in the formula. I won't flip back and forth a million times, but the atomic mass from phosphorus directly off the periodic table is 30.97. And we have 4 oxygens in the formula. And as we probably mostly know by now, because we've used it so many times, the atomic mass of oxygen is 16, and there's 4 of those. So when we add all that together, we get 163.94. In some of the more involved problems especially, we'll give you molar masses, but you do have to know how to calculate them. So that's how we get it for this compound here. And then we're going to use that as part of our conversion. But in problems like this where we ask you for moles, you have to look really carefully at we're asking you for moles of what, right? Because we're not asking you in this case for moles of sodium phosphate, we're asking you for moles of sodium ions. So we have to carefully account for what we're actually looking for in this case, which is moles of Na+. And then from there, we're going to do the set of conversions we need to get to that. So our given information is that we have 65.65 grams of the compound, which is Na3PO4. So as a first step, we can convert that into moles of the compound itself using this formula mass, this molar mass that we just calculated. So 1 mole of Na3PO4 has a mass of 163.94 grams. That's what we just calculated above. We're going to put that in the bottom because we want grams to cancel out. So that's going to cancel out. That gets us, though, into moles of the compound. But the common mistake that people would make in a problem like this is to stop here and just do this one step. But we're not looking for the moles of sodium phosphate. We're looking for the moles of sodium itself. And so for that, we have to look carefully at the formula of the compound and make sure that we have it correct. And what we see is that because it's Na3, there's going to be 3 moles of sodium plus in there for every 1 mole of compound that we have. All right, so we have to make sure we remember this last step here, or your answer would be off by a factor of 3, which would probably be the most common incorrect answer in a problem like this. So this last step is critical because we're looking for the moles of sodium plus, not just the moles of the compound. And so that gets us then to 1.201. 3 decimal places is what we're looking for, so that would be moles of sodium plus. We would just enter the number into Blackboard. All right, so don't forget that last step. This is a relatively straightforward mass to mole calculation to start with, but this last step here is one that we need to make sure we're accounting for things correctly. All right, questions on that? Yeah.
So when do you know when to like separate that into like Na and PO4?
So you would typically separate it in a situation like this where we can ask you something about usually either the number of moles or the total number of either one individual ion like sodium, or we could ask you for like the total number of ions in the whole thing, which would be now 4 of them because there's 3 sodiums and 1 phosphate. So if we're asking you about an individual ion in an ionic compound, you have to make sure that you account for the formula and do this last step. If we're just asking you for how many moles of sodium phosphate there were, you would stop here because this first step gives us that. But if you're asking about one of the ions in the formula or the total of how many ions there are, positive and negative, you have to make sure you look at the formula and do that last step. Yeah.
Okay, so like if it asks for grams of sodium ions, that's when we would do that last step of times 1 mole of sodium over the atomic mass, right?
In that case, it would be times the atomic mass.
Okay.
Because you want the grams on the top in that
right,
case.
right.
But yeah, you would do that. We don't usually ask for the mass of an ion because you can't really like weigh out an ion, right? It has to be paired with something else. But yeah, if you were to do something like, if you were to have something like that, that's exactly what you'd do.
Okay.
Yeah. You might do it more commonly for like, the mass of carbon in a covalent compound like carbon dioxide, something like that where it's covalent. You wouldn't usually do it for ion, but yeah, you're exactly right. All right, anything else? Okay, so let's go on to the next one, which is a mass percent problem going to empirical formula. So in problems like this, there's a pretty straightforward approach we're going to use, which is going to be, there's a few different ways of setting it up. One way would be to give you absolute masses of elements, and Another way would be give us mass percents, is what we have here. The most annoying way is if it's combustion analysis, where we say you're burning it and forming this much CO2 and this much water. That's a little bit more involved. But all three of those ways we can use to get to an empirical formula for the compound. Here it's in terms of mass percent, so whenever we have this, we're going to assume 100 grams of compound. So for given percentages, that's what we're going to do, because then that allows us to say, well, if we have 100 grams of the compound, the percentages tell us how many grams of each element we have. And so once we have the grams of each element, then we can go forward and just convert those masses into moles and get the mole ratio. So for each element, we're going to find the number of moles that corresponds to that mass. So for carbon, we have 65.4%, which means out of 100 grams, there's 65.4 grams of carbon. And we use the atomic masses to convert those each into moles. So carbon, hydrogen, oxygen. Carbon is 12.01, hydrogen 1.008, oxygen 16. So we're going to use those three atomic masses along with the mass percents of each to get the number of moles. So for carbon, 1 mole has a mass of 12.01 grams. That's straight off the periodic table. And so we get 5.45, sorry, that's moles of carbon. We're going to do the same thing for the other two, which are hydrogen and oxygen. So for hydrogen, we have 5.49 grams. And the atomic mass of hydrogen is close to 1. So you probably don't even have to do the math, but if you want to be real precise, what we get is 5.44 for that. And then for moles of oxygen, 29.1 grams of oxygen, that's the mass percentage of oxygen. And the atomic mass is 16. So we get 1.82. All right, so our numerically speaking, the empirical formula for this compound is C5.45, H5.44, O1.82. Of course, we want those to all be whole numbers, so we get those to whole numbers by dividing by the smallest, which is 1.82 for oxygen. So we divide all those by 1.82. And we get C3H3O. So for some of those, you might get like 3.001 or 2.999. But if it's that close to 3, you just round it in C3H3O, which is choice A here. All right, questions on that? The only other thing to be aware of on these problems, because it didn't come up here, is sometimes when you do this step here, you don't directly get whole numbers. So I'm going to write it in different colors so people don't think that it's actually part of the answer here. But let's say, assume we're not that we actually got an answer that looked like this. Sometimes you'll do that step and you'll get CH1.5O, for example. If you get an answer like this, where you do have decimals still after doing the normalization step up here, you don't want to just round this to C2H2O. That's way too much rounding. Only if it's really close to that whole number would you round. So in a situation like this, you need to find a whole number that you can multiply everything by to get rid of those decimals. So if it's 0.5, you're going to multiply by 2, and in that case, you would get C3H3O2. So that's just a word of warning about problems like this. Don't do too much rounding, and if after this normalization step you have one or more of your subscripts being pretty far away from a whole number, then you're going to want to find a small factor you can multiply everything by. All three of these have to get multiplied by the same number to keep the ratio the same. But if it's 0.25 or 0.75, you're going to multiply by 4. If it's 0.33 or 0.67, multiply by 3. 0.5 multiplied by 2 to get rid of those decimals and get them to whole numbers without doing too much rounding. All right, any questions on that? All right, number 9. So this is a balancing equations problem. And so in this type of problem, we're describing the reaction to you, so you do need to be able to again, convert names to formulas to be able to do this. We have barium phosphate reacting with sulfuric acid to form barium sulfate and phosphoric acid. What is the coefficient on sulfuric acid when the equation is balanced with the smallest possible whole number coefficients? So we need to get these chemical formulas right. And so for barium phosphate, barium is element Ba. It's an ionic compound. So barium is way down here. It's in the second column of the periodic table, so we would expect its ionic charge to be +2. So when we make that formula here for barium's phosphate, we're going to have, let me get all those written out here, up here first. So barium phosphate is going to be barium 2+, and as we saw in a previous problem, phosphate is PO4 3-. So the correct formula for this compound would be Ba3PO4 2. And then the second reactant is sulfuric acid. So we're going to have barium phosphate sulfuric acid is going to be from the anion sulfate, which is SO4 2-. And so for acids, you have to add the correct number of H pluses to the formula to balance the charge. So if you have a 2- charge, to make that into an acid, it's going to have 2 hydrogens, H2SO4. And then on the product side, we're going to have, they're going to form barium sulfate and phosphoric acid. So barium sulfate is going to be barium 2+ with SO4 2-. And so the formula for that would just be 1 of each to balance the charge, BaSO4. And then phosphoric acid, again, we have the PO4 3- anion. To make that into an acid, we would need 3 hydrogens. So it's going to be H3PO4. So those are reactants and products, and now we just need to put the coefficients in to balance. When you're balancing chemical equations, you can just do it for each individual atom if you want, and that would work. This one's going to be a little bit tough to do because you have oxygen like everywhere. There's 4 oxygen, PO4, SO4, SO4, PO4. It's all over the place. So when you have an equation that involves ionic compounds or acids, usually it's easier to just balance each polyatomic ion individually. So over here we have phosphate, over here we have phosphate, over here we have sulfate, over here we have sulfate. So keep those together and just kind of balance those as individual units, not trying to separate out all the different elements that are in there. I think that's helpful. And saying we have, barium on both sides. So if we look at this, then what we see is that this reactant has 3 bariums in it, and so we're going to need 3 over here, which requires a coefficient there. By doing that, we've now added 3 sulfates over here. SO4 2- appears 3 times now with that coefficient in front. So we're going to need 3 H2SO4s to make sure we have 3 sulfates on both sides. And then to finish this off, we would have, because we have 2 phosphates over here, we're going to need 2 phosphates over there, so that should get a coefficient of 2. And that should be balanced. We have 6 hydrogens on both sides, we have 3 bariums on both sides, 2 phosphates on both sides, 3 sulfates on both sides. Everything should check out at this point. So we want to know what is the coefficient then on sulfuric acid when it's balanced. So sulfuric acid is this one here. Coefficient would be 3 for that when we use the smallest whole numbers. So balancing equations is often just done by inspection, but I would encourage you for ionic equations especially, if you have polyatomic ions that appear on both sides, just balance those as a whole unit. Makes things a little bit easier sometimes. All right, any questions on that? All right, so that's just balancing, first part of getting into stoichiometry. Now the next couple questions are going to deal with stoichiometry. So number 10 here, if 3.25 grams of butane is the formula C4H10, is burned in the presence of O2 to form carbon dioxide and water, what is the mass of CO2 that forms in grams? All right, so first we need a balanced equation. Anytime we're doing stoichiometry, if they don't give us a balanced equation, we have to produce that before we can go forward at all. So for this one, we have butane, which is C4H10, and any combustion reaction is going to combine with oxygen O2, and the products are always going to be carbon dioxide and water. We told you that here explicitly, but that would be any combustion reaction would have this same format. Compound that you're burning plus O2 to make CO2 and water. And so now we need to put coefficients in. So typically for combustion reactions, because they do show up quite a bit in any general chemistry course, what I like to do is balance carbon and hydrogen first, because they typically will only appear one time on each side of the arrow, and then balance oxygen last. So we have C4, so that means we're going to need 4 CO2s on the product side. H10 is 10 hydrogens. To get 10 hydrogens from water, we need 5 of them. And then at this point, we can count how many oxygens we have. So on the right side of the equation, we have 4 times 2 is 8, plus 5 is 13 oxygens. So to get 13 oxygens from O2, you would have to have 6.5 or 13 over 2. For a stoichiometry problem, you don't have to use whole number coefficients. If you're happy with using fractions in there, you can stop there. That's a perfectly balanced equation, and you'll get the right answer from that. If you don't like fractions, or if we ever ask you to balance equation without fractions, what we would do is, again, multiply everything by a small whole number to get rid of the fraction. So if it's something over 2, you're going to want to double everything to get rid of the fraction. So every coefficient has to be doubled, or else they're not going to be balanced anymore. So you're going to have instead it's going to be 2C4H10. When we double the 13 over 2, it just becomes 13. And then on the product side, 4 doubles to 8, and 5 doubles to 10. So that would be the form of the equation that's balanced without fractions. Either one is totally fine for this problem. So from there, we can go forward and determine then what the question is looking for, which is how much carbon dioxide forms when we burn 3.25 grams of butane. So there's always a question in stoichiometry that you want to think about is, do we have to worry about limiting reactant here? And the key things to look for if you have to decide if you have to do that or not are, first of all, if we're giving you amounts of 2 or more reactants. There's only 2 reactants here, C4H10 and O2, and we're only telling you the amount of C4H10 and butane. We're telling you that there's 3.25 grams of that. For oxygen, we don't give you an exact amount, and furthermore, we even told you that it's an excess, so you don't have to worry about finding out what the limiting reactant is. You already know that it's C4H10 butane, so we can just start the problem without doing any extra work to get there. All right, so what we're looking for is the grams of CO2 when we burn 3.25 grams of C4H10. So in a stoichiometry problem, the first thing you want to do is you want to take the substance with the known amount and convert it into moles. So 1 mole of C4H10 has a mass of 58.14. We gave you that number here in the problem. That's the molecular weight or molar mass of that compound. So that cancels out grams. Once we have moles of one substance, the next step in any stoichiometry problem is going to be to convert into the moles of substance that we're looking for, which is CO2. And that's going to use the coefficients from the balanced equation. So we want moles of C4H10 to cancel, so that's going to go on the bottom. We want to find out how many moles of CO2 that corresponds to, and the numbers that go in these are going to be the coefficients. So 8 moles of CO2 are going to form for every 2 moles that react. And so then what we end up with is moles of CO2, but we're looking for grams. We have one last step, which is to use the molar mass of CO2, 44.02, also given to us, to convert into grams of CO2. And so all that comes across as 9.84 grams of CO2. We just asked for the number in Blackboard, so you would go 9.84 and stop there. All right, so that's going to be a typical stoichiometry problem. We don't have to worry about limiting reactant, but we do need to balance the equation first. All right, sorry, I was getting like a bunch of messages. All right, any questions on that? All right, so that's a pretty standard mass-to-mass stoichiometry problem. In this next one here, it's also stoichiometry, but it's going to be just a little bit more involved. So we're looking for the theoretical yield of gold chloride, gold-3 chloride, in this reaction shown below. The reaction is already balanced. One thing you can safely assume is that if we give you a chemical equation with coefficients, you can assume that it's balanced. We're not going to be evil and give you an unbalanced equation and throw you off that way. So if there's no coefficients, or if we don't give it to you, you have to balance it yourself. But if it's given to you with coefficients, just use it. Don't worry about us trying to pull the rug underneath from you on that. But here we're looking for the theoretical yield of gold-3 chloride when we have 29.6 grams of gold combined with 10.5 grams of HOCl in the presence of excess HCl. All right, so we have, in this case, 3 reactants. We're told that this one is an excess, so that's good. But we're given exact amounts of the other 2. 29.6 grams of gold and 10.5 grams of HOCl. We're trying to find how much of this product is going to be formed. So because we have mass amounts of two reactants, we have to first figure out which one is a limiting reactant. That's going to determine how much of this product can actually form. So there's different ways of handling limiting reactant problems, but the way that I'm going to do it is start by finding the moles of each reactant and then getting their stoichiometric ratio by dividing by the coefficient. So for each one, we're going to take the amount that we have, in this case 29.6 grams for gold, and we're going to divide by the atomic mass. So we didn't give you the atomic mass of gold, but it's on the periodic table, so we don't have to do any calculations. Au is down here, 196.97. So that's the atomic mass of gold, which would also be its molar mass. So 196.97 grams in 1 mole. So what we have then is 0.150 moles of gold. Now the other number that we need, though, to determine if it's limiting reactant is the stoichiometric ratio R, where we take that number and divide it by the coefficient. So the coefficient for Au is 2, so the stoichiometric ratio would be 0.075. Now the next one we have to do it is also for HOCl. So we have 10.5 grams of that reactant. Divide by its molar mass to get it into moles. We gave you that as 52.46. So grams cancels out, and then we get, let me make sure, I think that's 0.2 exactly, but let me make sure because I changed the numbers recently. All right, close enough, 0.0200. So that's the moles of the second reactant that we have the amount of to start with, and the ratio, stoichiometric ratio, is going to be that number divided by its coefficient, which is 3. So whichever one of these has the smallest stoichiometric ratio, capital R as it's abbreviated here, is going to be the one that is the limiting reactant. So that one's smaller, 0.067 versus 0.75. So this is our limiting reactant. And so that means whatever stoichiometric calculation we're going to do, calculating a theoretical yield like we are here, or eventually using that if we wanted to find percent yield, any calculation we do is going to start with the moles of limiting reagent. So what we're looking for in this problem is the theoretical yield of gold chloride, AuCl3, and so the calculation has to start with moles of limiting reactant. We have 0.200 moles of HOCl, and then from there we can go. So once we have moles of one substance, we can convert into moles of another using coefficients. So we have 2 moles of AuCl3 forming for every 3 moles of that react. So again, that's going to be mole ratios from the balanced equation. And then what we also have is we have to go to grams again. So same step as last time, we're going to use the molar mass of that, 303.32 grams of AuCl3 in 1 mole. And so that comes out to 40.4. And that would be the number that you would enter. I guess that one's 2 decimal places, and I did not write this out to 2, so whatever the second one is, put it in. But 40.4 would be the correct number of significant figures, and it would be done in this way. So you have to start with limiting reactant. If you had used gold as your starting point, you would have gotten a number that's bigger than this, which is not the correct number for this particular problem. All right, questions on that? All right, so that takes us to, I believe, the end of the Chapter 5 material. Everything else is now going to be Chapter 6. So you're kind of getting the idea that Chapter 6 is probably a little bit heavily emphasized on this one for whatever reason. I don't know the reasons for that, but we have 9 questions left, all of them Chapter 6. So it's a little bit heavier. Some of the stuff in Chapter 6 is still stoichiometry, so it relates back to other things, but that's where we're starting this. All right, so which of the following solutions would not conduct electricity at all? So when you're talking about electrical conductivity, you're classifying things as either an electrolyte or non-electrolyte. So anything that's an electrolyte would conduct electricity. Anything that's a non-electrolyte won't when it's dissolved in water. And so what we have are two subcategories of electrolytes: strong electrolyte and weak electrolyte. And for some problems, you may need to distinguish between these, and this problem is not critical that you do. But basically, electrolytes are compounds that when you dissolve them in water, they produce ions. And so a strong electrolyte is going to be one that when you dissolve it in water, it completely separates out into ions. And so there's two classes of strong electrolytes: either ionic compounds, when they dissolve in water, those that are soluble that dissolve in water are strong electrolytes, or if you have strong acids. So those are the two classes of strong electrolytes. We don't list strong bases as a separate category because all the strong bases we have are just ionic compounds anyway, so they would just fall into that first category. And then a weak electrolyte would be a weak acid or base. So when you dissolve a weak electrolyte in water, or when you make a weak electrolyte solution, you have sort of partial breakdown of the compound into ions. You're going to produce some ions in the solution, but not as many, so it won't have as high of an ionic concentration. But both of these are considered electrolytes, and both of these would conduct electricity. I can't draw brackets, let me just do a square one. So both of these would conduct electricity. Strong electrolyte solutions would typically conduct electricity better than weak electrolyte solutions because they have more ions. Both of them would conduct electricity. The ones that don't conduct electricity are non-electrolyte solutions. And that's going to be when you dissolve a covalent compound in water, one that's not an acid or a base. So if it's not an acid or a base, but it's a covalent compound that you dissolve in water, these ones do not conduct electricity. So in this problem, that's all we have to distinguish. Is it an electrolyte or is it not electrolyte? Which ones would not conduct electricity are going to be the ones that are non-electrolytes. So HNO3 is a strong acid, so it's going to be a strong electrolyte. So that one would conduct electricity in water. Calcium chloride is an ionic compound and it is soluble. So if we dissolve that in water, it will break up into calcium ions and chloride ions and conduct electricity. But this one here, if we have CH3, CH2OH, anything that just ends in OH like this is called an alcohol. We don't really need to know that it's called an alcohol, but those are all covalent compounds that are not acids. So when we dissolve those in water, this is ethanol, which is the form of alcohol that some people consume as a beverage. But anyway, that in water is a covalent compound. It doesn't break apart into ions. So this one would be a covalent compound non-electrolyte solution. All right, so that should be the one that we pick. Let's choose the other one, or look at the other ones as well. So KOH is an ionic compound, so it dissolves in water to make ions, potassium hydroxide. And then H3PO4, it's an acid, it's a weak acid, but it would still be a weak electrolyte solution as a result. So the only one that does not conduct electricity at all is choice C here, which is CH3CHOH, ethanol, which is a covalent compound. Now, in sort of deciding, which ones are covalent compounds and aren't acids, really the ones you should be familiar with are, things like this that end in OH. Just to be a little bit careful, though, if it ends in just OH, that makes it an alcohol, which makes it a non-electrolyte solution, totally covalent. There are some related ones that end in COOH. For example, acetic acid is one. These ones are acids. These are weak acids. Don't be confused by those. If it just has OH at the end, it's an alcohol, non-electrolyte. If it has OOH, COOH in particular, we call those carboxylic acids. Acetic acid is one of those, which has a CH3 at the beginning, and those would all be weak acids. So make sure you can distinguish those. But really, alcohols are the classic example that we would have of a covalent compound dissolved in water that gives a non-electrolyte solution. All right, questions on electrolytes? All right, next one here is dealing with mole conversions again, but this time in aqueous solutions, so we have additional things we have to know. So this one has a solution of 25.65 grams of calcium perchlorate, molar mass given, in 1.23 liters of total solution volume. What is the concentration of the ions, the perchlorate ions in particular, in molarity? All right, so for problems like this, we again need the correct formula of the ionic compound. So calcium is second column, so it's a 2 plus cation. Perchlorate, we have to remember, especially to get the charge right for this problem, is ClO4 minus. And so the correct formula for this compound to balance the charges would be calcium with 2 perchlorates. 1 2 plus cation with 2 1 minus anions. All right, so that's going to be the formula for that compound. So what we're looking for here is we're looking for the concentration in capital M, molarity. And we're looking for the concentration specifically of perchlorate. So again, for problems like this, just like similar to one we had earlier with moles, you have to really focus in on what are we looking for, either the moles of or the concentration of. Here we're looking for the concentration, the molarity of just the perchlorate anion itself, not the whole thing. So that means what we need to solve this are the moles of perchlorate divided by the liters of solution. And that's the definition of molarity, moles per liter, but specifically here it's for the perchlorate anion because that's the concentration that we're interested in. So what we're given in the problem is the volume already. We have the volume in liter, 1.23, so we don't have to do anything to get that. But we have to do some conversions to figure out how many moles of perchlorate are in this amount of the calcium perchlorate that we dissolved. So it's going to be a series of conversions starting with that given mass of compound. We'll convert that to moles first. When in doubt, convert to moles. It never hurts to do that. So convert that to moles by dividing by its molar mass, which is 238.98. So we have moles, but again, we don't want to stop here. The common mistake is to stop here. We're not looking for the molarity of calcium perchlorate. We're looking for the molarity of the perchlorate anion itself. So looking at the formula of the compound, which we had to get correct to start this, there are 2 perchlorates in the formula. So there's going to be 2 moles of perchlorate dissolved every time we dissolve 1 mole of that compound. So 2-to-1 ratio of perchlorate to moles of compound gives us 0.2147 moles of that ion. So that number is going to go up here into the numerator when we calculate the molarity. That's how many moles of perchlorate there are. So that number divided by the volume gives us the molarity of 0.175. And I guess you would just enter the number again, 0.175. All right, questions on that? So similar to the last one, we had to calculate moles of ions, but this time we just divide it by the volume to get it into a molarity. All right, number 14 here, we have 125 milliliters of water added to 225 milliliters of 0.254 molar NaCl, sodium chloride. What is the final concentration of NaCl? So sometimes with problems that deal with aqueous solutions, there's a little bit of confusion at the start of, is this a dilution problem? Is this a stoichiometry problem? Like which concepts, which formulas do I use? The key giveaway that it's a dilution problem, not stoichiometry, is that we only have one substance involved. So we're starting with a solution of sodium chloride, we're adding water to it, and we're just getting a different solution of sodium chloride with a different molarity. So if it's just one substance involved, that's just a dilution. We're just adding water to a solution to change its concentration. We don't want to think about, writing balance equations or doing mole ratios or anything like that. It's just going to be the dilution equation, which is simply M1V1 equals M2V2. So anytime you have a dilution problem, if you can recognize it early on, you know that it's going to involve this relationship on some level. So in this problem here, we're given the initial molarity and volume. That'd be M1 there, the initial concentration. V1 is the initial volume. And the only thing we have to be careful about here is that V2 is not directly given to us. Because remember that the volumes here are the total volume of the solution we have, not how much water we're adding or mixing together. It's the total volume here. And so for the V2, we're telling you that we're adding 125 milliliters of water. We're assuming the volumes are additive, and so it's going to be the sum of those two. We started with 225 milliliters, which was our initial volume. We added 125 milliliters of water. That's what we're told in the first sentence. And so the total final volume is going to be 350 milliliters if we assume that the volumes are additive. All right, so then what we're going to solve for here is the final molarity M2, which is going to be M1 V1 over V2. And now we have all the three things we need, M1 V1, and this here is going to be our V2. So when we plug those in, we get M1 is 0.254 molar. V1 is 225 milliliters. When we're using this equation, we don't really care which volume units we have as long as they're the same in the top and bottom. And then our V2 is going to be 350, also milliliters. So milliliters cancel out. We get an answer in molarity of 0.163. So we added water. The molarity did get smaller, so that makes sense. If it had gotten bigger, that means we messed up the math somewhere. And that's going to be a typical dilution problem. Okay, questions on that? All right, on to number 15. Number 15 deals with precipitation. So we learned about three different types of aqueous reactions: precipitation, acid-base, and redox. And this is the first of those, precipitation. So what we're asking here is which of the following mixtures will not form a precipitate? So in questions like this, I mean, you should know how to write balanced equations for all of these, but you don't have to go to all of those steps. You really just need to predict what are the two products that form when we swap the cations and the anions, and then are any of those insoluble? The coefficients don't matter in this case. We're just trying to predict if something insoluble will form. So in this problem here, all we have to do is look at the two reactants that we're mixing and just swap cations and anions to find out what the products are, and then use solubility rules to predict those. We don't have to write out the full balanced equations necessarily. So for choice A here, when we mix potassium chloride and silver nitrate, we swap cations and anions. So the potassium K plus is going to pair with nitrate NO3 minus to make KNO3. And then our silver, which is also +1, is going to combine with chloride Cl minus to make AgCl. So using solubility rules, we should recognize that all potassium salts are soluble. All those group 1A, lithium, sodium, potassium, rubidium, cesium. Did I leave one out? I forget. But anyway, all those group 1A cations are soluble. Nitrate is always soluble, so this one's definitely not going to precipitate, but this one would be. So silver is sort of one of the ones you should definitely focus your attention on, because most silver salts are insoluble, unless it's with nitrate perchlorate acetate, but nitrate being the most common exception to that. So that one's going to form a precipitate because silver chloride is insoluble. For choice B here, ammonium sulfate and lead perchlorate. Ammonium is NH4 plus combining with perchlorate ClO4 minus to make ammonium perchlorate. All nonmetals, but it is an ionic compound because technically it's going to be an ammonium cation with perchlorate anion. All ammonium salts, just like those group 1A ones, are soluble, so this will not precipitate in any situation. But the other one is going to be lead 2 plus with sulfate 2 minus, so it's going to form lead sulfate. Lead's another one like silver, where it's pretty much always insoluble unless it's with perchlorate or nitrate. So this one's going to be insoluble as well. So that would form a precipitate, choice B. For choice C, we have sodium carbonate and barium chloride. So sodium combining with chloride to form NaCl. We should all know that that's soluble in water, of course. But then if we have barium and carbonate, barium 2 plus, carbonate 2 minus makes BaCO3. And most carbonate salts are insoluble. Carbonate has, similar exceptions. It's pretty much always insoluble unless it's with one of those group 1A cations. So carbonates are usually insoluble, and so this one would be one of those. And then for choice D here, sodium hydroxide, iron chloride, sodium with chloride again, so it's also going to make NaCl. Clearly not going to precipitate, but then we have iron 3 plus with OH minus is going to make iron hydroxide. So one thing that's helpful to remember for hydroxides, the only hydroxides that are soluble come from those group 1A and group 1A 2A cations. So all the group 1A ones and some of the group 2s. So all the transition metal hydroxides, irons in the middle of the transition metal series, would be insoluble. So that's going to precipitate as well. So hopefully choice E doesn't have a precipitate, otherwise this problem has an issue. So when we do this one, we have calcium nitrate and ammonium chloride. So calcium is going to pair with chloride for one of the products to make CaCl2. and then ammonium is going to pair with nitrate. So most chlorides are soluble unless it's with pretty much silver and lead being the two major exceptions. So this one would be soluble, and then all ammonium compounds, all nitrate compounds are soluble, so both of these would be soluble. So in choice AE here, both of the potential products are soluble, so when you mix those solutions together, no precipitate is going to form. Every combination would be soluble. So that's going to be the answer here. It's the only one that does not involve formation of an insoluble product, which would then leave as a precipitate. So you do have to know those solubility rules. Some of them are, easier to deal with and come up more often than others, like silver and lead are all over the place in these types of problems, but make sure you're familiar with some of the other ones as well that are a little bit more nuanced. Okay, any questions on that? All right, 5 more. All right, so this one asks another sort of aqueous reaction type problem. What are the spectator ions when aqueous solutions of barium nitrate and sodium phosphate are mixed together? So as we're told here in the answer choices, barium is 2+, so barium nitrate is going to have 1 barium and 2 NO3 minuses. So if we start with the formula equation here, we're going to have barium nitrate combining with sodium phosphate, which is Na3PO4, sodium plus phosphate 3 minus. And then the products is going to be 2 ionic compounds being combined. So just like the last problem, we're going to just predict the products as being the other ionic compounds that form when we swap cations and anions. So barium with phosphate, I think we saw this formula earlier, Ba3PO4 barium 2 plus phosphate 3 minus. And then we're going to have sodium pairing with nitrate to make sodium nitrate. To identify spectator ions, we don't necessarily have to do the full balancing, but let's go through and do that just to see how it works. And so to balance these, there's 2 other pieces. We have to figure out which, if any, of the products are soluble and insoluble, and then also add coefficients. So first, from solubility rules, we see that this compound here has phosphate. Phosphate's a lot like carbonate. Most of the compounds with phosphate in it are insoluble, unless it's like sodium, lithium, all those first column cations. So if it's a group 2 phosphate, it's going to be insoluble, and so this one would be our precipitate here. Sodium nitrate, all sodium salts, all nitrate salts are soluble, so that's going to stay in solution. So now we have some coefficients to add because we have 3 bariums over here, so we need a 3 there. Now we have 6 nitrates, so we need a 6 there. We have 6 sodiums, 2 phosphates, so we need a 2 there. So this one does have some coefficients, more than you usually see for a precipitation reaction, but that would be the fully balanced form. We don't really need all the coefficients again just to identify spectator ions, but we're just going to go through that. Now to figure out what the spectator ions are, we have to figure out, there's a couple ways to do this, but the sort of rigorous way, I suppose, is to separate everything out into ions. Everything that's aqueous is going to be dissolved in solution, separated into ions, and we can write it out in that way. So on the left side, we would have 3 barium 2 pluses and 6 nitrates from barium nitrate, because we have 3 times 2 is a total of 6. From sodium phosphate, we have 6 Na plus and 2 phosphates. And then on the product side, this is our insoluble product, our precipitate here. So that one's going to stay together. We're not going to separate that because it's insoluble. And then we have 6 sodium pluses and 6 nitrates. Never have quite enough room for these. All right, so that's going to be the total ionic equation where we've separated every aqueous substance into the individual ions that it would break up into. And then those that appear on both sides are going to be our spectator ions. So NO3 minus, 6 NO3 minuses on both sides. And we also have 6 Na pluses on both sides. So sodium and nitrate are the spectator ions. That would be answer B here. And then the net ionic equation would be the one that just removes the spectator. So it would be 3 barium 2 plus 2 phosphates. So this is our net ionic. We didn't have to do all this for this problem. I'm just kind of showing it to you for completeness. To identify spectator ions, you just look for the ones that are aqueous on both sides. So nitrate is aqueous here, aqueous there. Sodium, aqueous there, aqueous there. So both sodium and nitrate are dissolved in solution on both sides, and that makes them the spectator ions for this reaction. All right, any questions on that? All right, the last one that's not a redox problem, so there will be 3. All right, we have, this is a typical titration problem because we have a sample of an unknown diprotic acid with 2 acidic hydrogens. So all that word salad tells us, diprotic acid, 2 acidic hydrogens means that the general formula for this acid would be H2X, some anion X with 2 hydrogens on it, meaning that it's 2 acidic hydrogens, as we said. And we neutralize it with 0.375 molar NaOH. It takes 40.9 milliliters of the sodium hydroxide to neutralize it, so what is the molar mass? So in titration problems like this, you're going to typically calculate moles on some level, and it's just what you do with that that varies from problem to problem. So if we're looking for a molar mass, or a molecular weight as it's often abbreviated, the 2 things we need are the mass of the acid and the number of moles. So again, in a titration problem, we're usually going to use stoichiometry to figure out the number of moles, and we're going to do something with that depending on what the problem is asking. Here we're going to just divide the mass by the moles to get the molar mass. So in this problem, the mass of the acid that we have is directly given to us, 2.34 grams. And so we just need to figure out the number of moles and divide the 2. In a titration problem, it's just, it's just a fancy way of saying stoichiometry. There's really nothing different at this stage. We're just going to write it out as a balanced equation and do stoichiometry to figure out the number of moles of that acid. So we have H2X reacting with NaOH in an acid-base reaction. We don't care too much about the product side in a titration because we're just measuring out the amounts of acid and base that react with each other. But what we would get is water plus an ionic compound, which would be Na2X. So to balance this, though, especially on the left side, it's important. We have 2 H pluses from our acid. We only have 1 OH minus from the base. There need to be equal numbers of those, so that requires a coefficient of 2 here to make sure that each H plus is neutralized with OH minus. By doing that, we get a 2 in front of water as well. We don't care so much about the right side, but that would be the full balanced equation. With this balanced equation, and especially with this correct 1-to-2 ratio on the left side, we now have everything we need to calculate the moles of acid, which we're going to use in that calculation above. So to do this, we're going to start with the volume and molarity that we know. So we know that the NaOH solution required 40.9 milliliters, and it has a molarity of 0.375. So those 2 together allow us to find the moles of sodium hydroxide. 40.9 milliliters of the NaOH solution. Then remember that molarity is moles per liter, so 0.375 moles of NaOH per liter, or as a shortcut, you can write it as 1,000 milliliters, so that milliliters directly cancel out. So in any stoichiometry problem, once we get moles of one substance, we can find moles of the other using mole ratios. And so the coefficients we want NaOH to cancel, so that's going to go on the bottom. We want to find out how many moles of the acid there are. The acid has a coefficient of 1 in front of it. The base has a coefficient of 2. And so it's going to be a 1-to-2 ratio. And that gives us then 0.00767 moles of the acid H2X. And so that's the number then that's going to go back up into here, dividing the mass by that number to get molar mass. And so that comes out numerically to 305.1 grams per mole, and the number would be 305.1 that you would enter in. All right, so that's going to be a typical titration problem. It's just knowing what to do with the number of moles. The way that we calculate the number of moles is typically always the same. Molarity and volume of one of the reactants gives us the moles of that reactant. Mole ratios gives us the moles of the other reactant that would react with that. I did get some questions recently from students about, can we use M1V1 equals M2V2 for these types of problems? There are some instructors that teach it that way, but I would not recommend doing that because that only works if it's a 1-to-1 reaction between the acid and the base. So here it's a 1 to 2 reaction, so if you use M1V1 equals M2V2, you would not get the correct number of moles of acid. You get a number that's off by a factor of 2. So I would suggest setting it up always as a stoichiometry problem in the way that I did here, where you're using still the molarity and volume of the one species to get the number of moles, but then you have to make sure you account for the mole ratios to be able to get the correct number of the other one that's reacting with it. All right, any questions on that? Okay, the last thing we have to go through then is going to be redox numbers, redox equations. I've explained this to some of the students that I talked to. Basically, these question banks that we have persisted over many years, and we tweak them, we modify them from time to time, but they kind of have an origin of several years ago at least. And the person that put together a lot of these questions loved redox equations. So just to be prepared, you're going to have 3 questions on the exams that deal with redox. I mean, that's how it is in the review. That's how it's going to be in the exam. The first one of those 3 is going to likely be something like this. It's not going to involve balancing an equation, but it's going to be something about oxidation numbers or identifying the oxidizing or reducing agent, something like that. So that's what we're going to have in this first one here, and then we'll have to balance 2 equations for the last 2. So this one just deals with oxidation numbers. Which of the following is the correct oxidation number for nitrogen for all the choices that we gave? So let's just calculate it for all of them and figure out which one is right. So if we have HNO3, reviewing the rules for oxidation numbers, this is a covalent compound with all nonmetals, and so in covalent compounds, with rare exceptions, you'll have oxygen being -2, hydrogen always +1 if it's in a covalent compound. So then we're going to get the nitrogen by difference. So all these have to add up to 0 because it's a neutral compound. So 3 minus 2 is a -6, +1 is -5. That leaves +5 for nitrogen, so they all add up to 0. So in HNO3, the oxidation number for nitrogen is +5, so that one is incorrect. In letter B, we have NO2, nitrogen dioxide. And again, in covalent compounds, I guess I should give you the exceptions for oxygen because people wonder about those sometime. So the oxygen exceptions are obviously O2 because it's an element. The oxidation number is 0. And then in H2O2, oxygen is bonded to itself. And by balancing the oxidation numbers, you get an oxidation number of -1 for oxygen. And there's also this really weird one that you might see, but very uncommon, OF2. Fluorine's -1, that means the oxidation number for oxygen is +2 in this. I'll write it above oxygen so you can see, -1, 0. So these are the exceptions of compounds where oxygen would not be -2. I can't really think of any other that you're likely to see. So in NO2, any other covalent compound besides these 3 up here, it's safe to assume that oxygen should be -2. So if you have 2 -2s, that's -4. That means nitrogen should be +4 in that compound. So that one's also wrong in the answer choice. Letter C, NCl3. So when chlorine is the outer atom in a covalent compound like it is here, it's going to be -1. Only if it's the central atom would it be something different than that. So -1 for chlorine, 3 -1s is -3. And then that one would end up as +3. So again, that one is not correct. And then finally, for choice D, if we have N2, anytime you have just a single element in the formula and no charge given, so N2 or any element that's just singular like Na or Ag or whatever, but any element or compound that just has one type of atom in it, no charge, is always going to have oxidation number of 0. That's the only time the oxidation number is 0. Okay, so that one would be 0 whenever it's a neutral element, any form of that element. And so this one is also wrong. So the correct answer for this problem is E, none of the above. All 4 of those answer choices have the wrong oxidation number. Now I realize that there is a psychological barrier to picking none of the above as the answer, but if you trust yourself that you did the problem right, don't be afraid to, because it's not impossible. And this is one where none of the above would be the correct answer. All 4 of those have the wrong oxidation number for nitrogen given. So any questions on assigning oxidation numbers? All right, the last thing we have to do is go through balancing. So I missed this class. This class would have been taught by Professor Larson, but there's a recorded video on it. So let's go through that here. So this first one here, we have what is the sum of the coefficients when we balance the whole thing? So we're going to have to balance this whole thing for this problem. All right, so what we have, I'm going to have to write this out again and give myself enough room to do this. H plus MnO4 minus NO Mn2 plus NO2 and water. So when we're using the oxidation number method to balance redox equations, the first thing we need to do is assign all the oxidation numbers of every element, every atom on both sides of the arrow. So we have to be pretty proficient at doing that. So H plus is going to be +1. Anytime you just have an ion by itself, the oxidation number is just the charge. MnO4 minus is a bit of a tricky one, but it will come up from time to time in these. It's called permanganate. It's commonly used in redox reactions. So oxygen is still going to be -2, just like it almost always is, except for those rare exceptions that I talked about. So 4 minus 2s is -8. The sum has to be -1 because of the overall charge, so that leaves manganese at +7. So +7, 4 minus 2s add up together to be -1, which is the charge. For NO, similar to NO2, the last one we just did in the last problem, -2 for oxygen means that nitrogen has to be +2 to balance that out to 0. Mn2 plus is nice because it's just an ion by itself, so the oxidation number is equal to the charge. NO2 we did on the last problem also. -2 for oxygen, 2 minus 2s is -4, +4 for nitrogen. And then finally, our good friend H2O, -2 for oxygen, +1 for hydrogen. No thought involved in that one. Okay, so those are all the oxidation numbers. The next step to balancing this is to find the ones that are changing between the left and the right side of the arrow. So manganese is going from +7 to +2, so that one's different. And then nitrogen is going from +2 to +4. So those are the two that are changing. All right, so that's going to be the ones that are changing. We have to count out how many electrons that would be. The number of electrons that are involved in that is going to be the difference in the oxidation numbers. So when manganese goes from +5 to +2, that's a difference of 5 electrons. It's gaining 5 electrons. For balancing, we don't really care if it's gained or lost, but this one will be gaining 5 electrons because the oxidation number is getting smaller. And then nitrogen going from +2 to +4 is a difference of 2 electrons. And so that's going to be losing 2 electrons. But the number of electrons is what we care about, that difference in the two oxidation numbers of 2. All right, so we have 5 and 2. We need the number of electrons to be equal, so we have to multiply one or both of them by a factor to get them to be the same. So the least common multiple of 5 and 2 is going to be 10. So if we double this one, that gives us 10 electrons, and if we quintuple that one, that also gives us 10. So by multiplying that by 2 and that by 5, we get 10. So that means the ones that are multiplied by 2 need to have coefficients of 2, and the ones that are multiplied by 5 need to have coefficients of 5. And then the last step here is going to be to balance everything else by inspection. All that's left is H plus and water. Once you set the coefficients for the ones that are involved in the changing oxidation numbers, the ones that are involved in the redox process, you don't want to adjust those coefficients anymore. It's going to throw everything off. So leave those the same. We're just going to look at now water and hydrogen, H plus, to make sure that everything adds up correctly. So we'll do oxygen first. So on the left side here, we have 8 plus 5 is 13 oxygens. On the right side, we have 10 from NO2, so we need 3 more. So that means we need 3 waters here to make sure we have 13 on both sides. By adding 3 waters, that gives us 6 hydrogens, so we're going to have 6 H pluses to make sure that hydrogen is the same on both sides. All right, so that's all the coefficients. Now we just have to add them together to report the answer for this problem. The sum is going to be 6 plus 2, which is 8, plus 5, which is 13, plus 2, which is 15, plus 5, which is 20, plus 3, which is 23. So choice A would be correct for this one. Again, there's no real benefit to knowing the sum of the coefficients. It's just how we often ask you to answer questions in Blackboard, just to make sure that you balance the whole thing. And that's what you had to do here to get that number. All right, questions on that one or anything about balancing redox equations before we tackle the last one? Yeah. Yeah, so for H2O, we usually, the order that's helpful to go in is we're going to use water to make sure that oxygen is balanced on both sides. So after adding all the first 4 coefficients, what we had was 2 times 4 is 8 plus 5 oxygens on the left. That's 13 oxygens on the left. On the right side, we had 10 from NO2. So we needed 3 more to make sure there was 13 on both sides. So those 3 are all going to come from water. So by adding a 3 there, that gives us 13 oxygens on both sides. 3 waters has a total of 6 hydrogens. That's where the 6 here came into play. All right, any other questions? All right, we'll do one more, which we're going to follow the same approach. This one is, the formatting is all screwed up, unfortunately. I don't know how that happened. Those should all be subscripts. Let me just write it out again with subscripts. I don't know what happened there. I think I tried to edit this slide at the last minute, and somehow Adobe changed my subscripts to superscripts. So not cool, Adobe. All right, so let's write it out again correctly. There should never be superscripts in chemical equations anyway, as you guys all know, so that should immediately raise a red flag. All right, similar story as the last one, but there's one little difference here. Okay, so in this problem here, let's start by assigning oxidation numbers like we always do. So chromium chloride, 2 Cls are -1, and that means chromium has to be +2 in that compound. HNO3 we did earlier, but as a reminder, we have -2 for oxygen and +1 for hydrogens. That's -6, +1 is -5. We need a +5 on nitrogen for them to all add up to 0. For chromium nitrate, the important part here is that the chromium is now +3 because we have 3 -1 anions, so our metal is now +3. For nitrate, it's helpful to remember that if we're just taking off an H+, so here we have HNO3, nitric acid, and over here we have NO3-, which is the anion of that. We don't change the oxidation numbers by doing that. You could calculate them separately if you wanted to, but you're still going to get -2 for oxygen, +5 for nitrogen. So they don't change their oxidation numbers just when you put an H+ on or take one off. If for HNO2, though, we have a different formula now. So when we have -2 for oxygen and +1 for hydrogen, -4 +1 is -3. So that means this nitrogen is now +3. And then for water and HCl, we have +1 and -2. And then +1 and -1. All right, so that's going to be all the oxidation numbers. So for this one here, we find the ones that are changing to start with. So chromium is going from +2 to +3. And then we have nitrogen going from +5 to +3. Now this is one of those weird ones though. We came across one of these in class where we have nitrogen and nitric acid going from +5 to +3 as it converts to HNO2, but we also have some nitrogen on the product side that's staying at +5. So we're going to have to add additional HNO3 to make sure we have the correct total number of nitrogen atoms on both sides. So however you want to handle that is fine, but I like to, in this case, split them up into 2 pieces. We're going to balance some HNO3 based on the number of electrons that are changing from HNO3 to HNO2, and at the end we're going to have to add more HNO3 to make sure that we have the correct total number of nitrate ions or nitrogen atoms, however you want to think about it, on both sides. So I'm going to actually split this up here. It's a little bit, some people don't like doing this, but I have shown it before, where you're going to take, for HNO3, we're going to have part of it that we balance just by getting the number of electrons right, another part that we're going to balance at the end to make sure that the atoms are all balanced, and we'll do that in 2 pieces since we're going to do that in really 2 different steps, and then we'll combine them back afterwards. All right, and so as we said, chromium is changing from +2 to +3. So that's a 1 electron change, a difference of 1. Nitrogen is going from +5 to +3, so that's 2 electrons. So to balance those out, all we have to do is just double the coefficients on chromium chloride and chromium nitrate. So those are going to get coefficients of 2. And then HNO3 and HNO2, the ones that we're balancing for the redox change, are going to get coefficients of 1. So those coefficients are set. Now we just have to make sure that we have the correct number of atoms on both sides. So we have to do a little bit more by inspection. So what we find is that in this product here, chromium nitrate, sorry, it should be 3 nitrates, not 2, sorry. There's 3 nitrates per formula unit and a coefficient of 2, so a total of 6 nitrates in this compound here with a coefficient of 2 out in front. So we're going to add 6 more HNO3s to make sure that we have the correct number of nitrate ions on both sides. That one's just going to make sure that the atoms are balanced. And then we have to do the rest by looking at oxygen and chlorine to make sure they're balanced on both sides. And so for what we have for chlorine here is that on the left side we have 4 chlorines, 2 each for this compound here, so we need to have 4 HCl's. And then for oxygen, we have to make sure the number of oxygens is the same on both sides. That's where water is going to come into play. What we have is over here, if you want to count them all together, we have 3 plus 18 is 21. Over here we have 18 plus 2 is 20. Or alternatively, we know that the only one that's losing oxygen is this HNO3 to HNO2. That's losing 1 oxygen, so we need 1 more water over there. And then hydrogen should be the same now on both sides, if we did everything else correctly. So when we add this all up together, what we get is 2 chromium chlorides, total of 7 HNO3s. 1 of them we added to balance the number of electrons, 6 others we added to keep the number of atoms balanced, and then we have chromium nitrate, 1 HNO2, 1 water, and 4 HCl's. So that one was a little bit more involved because we had that extra little piece we had to do with nitric acid. But it should all be balanced now. We haven't checked hydrogen yet, but what we have over here are 7 hydrogens, and over here we have 1 plus 3 plus 4 is also 7. So we didn't check hydrogen, but it does work out if everything else was taken care of. All right, so that's the final one, and we want to know the sum of the coefficients on the reactant side, which is going to be 2 plus 7, which is 9 on the reactant side. All right, so you have to decide for yourself what your favorite approach is for dealing with this situation here, where nitrogen was changing its oxidation number, but also in some cases was staying the same. So you had to basically serving 2 roles. It was the oxidant in this case being reduced to HNO2, and it was also providing the counterions for the product over here. All right, any questions on that one or redox equations in general? All right, any last questions before we wrap this up? Okay, so feel free to contact me with anything you want to go over as your exam approaches. I should be around for, I could post this on Blackboard if I remember, but I'll be around for at least some other day on Monday, probably before 2 p.m., late morning, early afternoon, I'll probably be there. So if you need to stop by Monday, I'll have regular office hours on Tuesday. And so best of luck with your exam, and I'll see you guys all next week.